rang the bell twice. Did you hear it?
Yeah.
Well, you're here, of course. Okay. Well, I mean, what can I do? I mean, I can't force people to listen to the bell. So Dong, who is in Barcelona for the time being, is on his sabbatical. Dong Yang, he's talking. He also offered to give a talk about some recent results, and so it's also information theoretical concepts to do with so-called potential capacity, which I think is something that he introduced, or that goes back to some ideas of Charlie Bennett that probably were never really written up. But okay, I mean, you must be the first one to have any kind of decent result on it anyway. So please.
Okay, first thing. First, thanks the organizer to provide me the opportunity to give talk here. I want to talk about some concept about potential capacity of a quantum channel. And first, let me define what is the potential capacity. Definition. So given you a channel, you can define the potential classical capacity and potential quantum capacity in this way. And here, this is called potential classical capacity, and C is the classical capacity for the channel. For the quantum case, it defined similarly. So why we would like to define such a quantity, because we don't know much about the capacity here and here. Then, what do you define such a quantity? The reason is that we know from the non-additivity, we know that generally of course, what we know about the classical case and the quantum case, maybe I should we know that the here similarly we write and here it's the Kn is the whole level quantity of the channel defined as and for the quantum case, In is the one-shot quantum capacity. We know that from Hastings result, we know that generally this is larger than and there exists the channel such that here the strict larger holds, and for the quantum case from the superactivation or some other channels, we know that there is channels such that the strict here hold is there here the strict larger hold, and also for the quantum case we know that if you and also we know this, but for the quantum case we don't know. We don't know this, but it is believed it should be true. So anyway, with this we know because when because the strict larger here strict inequality here require the entangled input to obtain large capacity. So it means that entangled input can help. Then we would expect that could the entangled input help us such that if the quantity here is not achieved the maximal possible capacity, then by some other channels it can help to obtain the maximal value. So that's the motivation to define this quantity, and because we know due to the non-additivity, the channel capacity is not the unique quantity that characterizes the ability to transmit information. So, but when we take the supreme over the contact channels, then this quantity does not depend on any other channel. So the quantity in some sense characterizes the potential possible ability to transmit information. If you consider classical, then that quantity, and if you consider quantum case, this. But just the definition, we cannot tell much. And in this talk, in fact, I cannot tell much about this quantity, but just to provide upper bound for this quantity and this quantity. So, in order to provide the upper bound for these two quantities, we need some similar definition to those definitions there, but it is defined in the single copy case. I mean, Similarly, you can define the potential whole level quantity in this way. And of course, you can define something like this for the quantum case. And another thing is that this quantity is subadditive. By subadditive, I mean that similarly, for this quantity, it is also subadditive. And from definition, it is very simple to see this, because this is something like minus, then you minus plus supreme then this will give you the XPM. Here will give you the N. Similarly, here we also have and then
The same is true then for C and Q, no?
yes, exactly. Yes. Then we have a theory of inequality here is X N as I mentioned that in this talk I would provide some upper bound for this quantity and this quantity. In fact, I would provide upper bound for the quantity here and here. In the following, I will show that XPN is upper bound by and a G function. In the following, I will explain what's the G function here. And for the quantum case, it is upper bound by the entanglement formation of the capacity of entanglement formation. I will explain what it means. First, we provide the way to obtain this upper bound. according to the definition, here is okay. Let's just to look at the channel N. Here is this is from A to B is the channel N, and here is the isometry of the channel, and from A to E it is the complementary of the original channel, and use the MSW relation. X N can be written as maximum rho A and rho A minus here is the entanglement formation of between B and E. And you can see it is very similar to this form, but it is here it is a different correlation function between B and E. To find the upper bound for this quantity, what we consider is okay, we just consider the something like this for arbitrary A1, A2. Here is 1, 1, 1, A2, M. Minus F and we know that this is less than and the key point is that we would like to obtain an upper bound here in this term in the form that we should remain and then there's some function here. I mean, to provide upper bound for this quantity, because we this is something like the Km, the half capacity of M, and we would like to minus this quantity from so we need a term like this. And in fact, there is already inequality satisfied the relation here. that asserts and what's the T function? T function is it is defined as a mixed state ensemble that realizes the average state. And for this function here is in the literature it's called the Henderson-Vedral classical correlation function. It is defined for a bipartite state. It is and where that means you perform a measurement of his side, and then the state of B is reduced to an ensemble of state. Then use the whole level quantity of the ensemble state to measure the correlation. QG is trees. Here is a general POVM measurement. And here is the normalized reduced state when you obtain the result of G. And we know that for such a function here, this equality holds. So then naturally we obtain an upper bound of this quantity. And still we know that this quantity has some nice property that asserts the t function is larger than 0 if and only if rho BE is entangled. That means if the bipartite state rho BE is separable, then this quantity is 0. So with this, we can assert that if the classical capacity of a channel is not maximum, or if the channel is not perfect, here we mean perfect if the channel capacity is the maximal possible value. So curly is if is strictly less than the maximal value, then this quantity is strictly less than the maximal value. The reason is that, in fact, we with the upper bound here, we could prove that if this quantity is equal to the quantity here, we will obtain that even for the single use, we can obtain the quantity here. The reason is very simple, because this function is, in some sense, it is a faithful function for the rho BE. If this quantity is the maximum value, that means it must be 0. And because this is 0, that means rho BE must be separable. And rho BE is separable means EF should be 0. And then we know that something here is 0 and it is the maximal. So we obtain this result. Okay, this is the classical case. For the quantum case, we okay. For the quantum case, we would obtain this quantity, and here the EF is the capacity of entanglement formation defined in such a way: maximum plus here R is the reference system, and okay. This is the maximal entanglement formation that can be created by the channel. Before we obtain this upbound we would like to record some idea to obtain an upper bound for a quantum capacity. And we know that how do we obtain an upper bound for a quantum capacity of channel? And people know that giving you a channel and usually we do not know how to find the upper bound for the quantum capacity of the channel, but we can lift the channel up to a degradable channel. For degradable channel, I don't know, maybe everyone knows the degradable channel? Okay.
So I have a quick question.
Okay.
This upper bound it's a single letter upper bound. You don't need the regularization.
Yes, exactly. Yes. Here is the channel, and we have the isometry from BE, and a channel is degradable if there exists another quantum operation so that the channel can simulate the complementary channel. Then here N is called degradable channel. And people know that for the degradable channel, the quantum capacity is additive. That means the quantum capacity of a degradable channel is reduced to the singulator formula. So to find the upper bound for the quantum capacity, we need to lift the channel to the degradable channel. Of course, there are many different ways to lift up a channel to a degradable channel. But here you can see what we want to obtain the upper bound for the potential capacity. We would like something strong additive. By strong additive, I mean for some special channel, for any other channel, this should be hold. I mean, M arbitrary, but we should choose some special class of the channel N. Then and we know that to obtain a strong additive channel, it is not enough to lift the channel up to the degradable channel, because from the superactivation, we know that the symmetric channel, which is a degradable channel, but not satisfy the strong additive. So we need lift the channel up further. And in fact, there exists a special class of degradable channel called Hartmann channel, whose quantum capacity is strong additive. If N is Hartmann, then we have a strong additive. A channel is called Hartmann channel if its complementary channel is entanglement breaking. So if this channel is Hartmann channel, that means this channel is intent breaking. Then we know that intent breaking can be represented by the cross operator as this. Here, here this vector is unnormalized. So the original channel, the isometry can be here is this is our metric of the channel. And from this, we could obtain that for any other channel whose isometry is U. And for a arbitrary input where I mean U, A1, A2, this is a general input, and the output state can be written in such a form. And now let's look at the coherent information here. That means we look at the quantity here, and it is equal to minus and here we know that we could we could copy the B1 into another register, so we have a B1 prime here, and then this conditional entropy should less than the because here B1 prime can be obtained from the from B1 by equivalence operation, and this term is minus yes. d minus yes, and this term is larger than this term because here B1 prime can simulate the state here. So then we have the quantity here. And this term is just the coherent information of the channel N, and here is something like the average coherent information of E2 E. And then we know that it is less than the sum. And the other direction is true. I mean, you just use the product input state. So we could obtain our upper bound for this quantity if we lift the N to the Hartman channel. Now, how could we obtain a Hartman channel, or how could we lift up the N to a Hartman channel? That means you get some information from the environment state to the system B. And we don't know the general way to take the information to the from the environment to the system, such that the environment, such that from the input state to the environment, it is in time breaking channel, but we know some special way to obtain that. I mean, just copy the environment state and take the copied information to the system. That is a special way to lift up the channel N to a Hartman channel. I mean, for this channel, we know the cross operator here, and how we know the simple way to lift up the to a Hartman channel in such a case. Just add yes. Just add orthogonal flag to the cross operator, and in this way we could know that because this channel is of a very special form, it is very simple to compute the coherent information, coherent capacity for the channel. It is additive, so capacity will reduce to the singulator form, and it is something like here it should be maximum and here you need to normalize this state, and Pi is the normalization coefficient of this state. So we know because this is for this channel, it is Zhong-anti. So we know this. In fact, in this form, we just written the particular cross operator. And to obtain a better upper bound, we should take the infimum for all the possible cross operator for the channel. Infimum and then we notice that this quantity is the same function here, just that the mini and the supreme in different order. And the other result is that, in fact, we can swap the mini infimum and the supreme here. Though it is not obvious, but from paper by Mariberta, Fernando Brando, Matthias Cradam, Stephanie Werner, in time cost of quantum channel, their results imply that the order can be interchanged. And then we obtain the result here. And from the upper bound, we could assert that if the similar result, if a quantum channel is less than this, then this should be less than the maximum. And in fact, we prove that if it is equal to this, then just for the the one-shot quantum capacity, it is the maximal value. Then how could we obtain this? And just from the upper bound here, we know that but what this should be the something the, and we know that if this here equality is true, then that means each member of the state should have the same reduced state. That means here is B, then each rho I E should the maximum mix state. Then from this one, we know that for the output state plus the reference system and the environment state, it is a pure state. The pure state is up to unitary transformation, or R. It can be written in such a form. So in this form, you can find encoding subspace such that for another state, then its output state will be and here it is sim form. So we obtain the result here. So that means if the quantum capacity is not the maximal value, then under any other channel assistance, it cannot be activated to a perfect channel. So this is the results. And there is some questions. Maybe you already noticed that in fact here the definition can be extended to the private capacity, but I did not say anything about the private capacity. The reason is that by far I don't know whether the Hadamard channel is strong additive for the private capacity.
I think it is. It is.
It is. Why?
Talk about
Okay. Because I tried, but failed to obtain that. Okay, good. Okay. And the other question is that because we don't know much about that quantity, even we don't know the continuity of that quantity. But it seems that it should satisfy the continuity, though we cannot restrict the dimension of the M, but it is something. It is a form like the conditional quantity. So maybe it does not depend on the dimension of the channel M. So I just stop here. Thank you very much.
So do you know how tight these upper bounds are? I mean, do you know the cases where they are equal? Is this inequality?
If you take in the Hadamard channel, it is equal.
But for the second one, no.
For this.
Because the entanglement of formation in general is larger than the.
Okay. See, for the channel, for the special Hadamard channel. I mean, for the channel with the flag.
Oh, well, you have the flag already. Okay,
Yes.
Sure.
Okay.
Okay. Fine.
In fact, from the in-time code of the con channel for the channel, the Zhong commas holds for the channel, though it is.
Yeah. Let's see. Sure. Okay. Any more? If not, then thanks again. Tom.